Welcome again to magnetostatic fields. In this video, we will discuss about an application for vector magnetic potential, which is the magnetic field calculation for a circular loop. The problem setup is as shown here. Simply, we have a circular loop placed in the xy plane. It has a current I, which equals to I naught in the direction of phi, and would like to calculate the resulting magnetic field at a point P r theta phi. In order to calculate the magnetic field, first we need to calculate what is called vector magnetic potential. Then from the relation between the magnetic field and vector magnetic potential, we can say that H equal to 1 over mu curl A, which is the magnetic potential. So how to solve this problem? Simply we apply the law which we have derived in the previous videos. A equal to mu over 4 pi integration of I over magnitude R. This is our R. dl. First for dl, since we have the current looping in a circle, then what is it changing is phi. Then dl will be simply um, d phi, but of course don't forget to multiply by a, which is the radius of this loop. To distinguish between our phi, where we want to calculate the field, and phi, where the current loops, we will represent I as I naught in the direction phi dash. Phi dash we can rewrite in the Cartesian coordinate as minus sine phi dash in the direction of I plus cosine phi dash in the direction of j. Now we need to understand what is our point. We have 2 points. The point where we calculate the current here, for example, and this will depend on phi and a. So say this is m, and m is a cosine phi dash, the x coordinate, and a sine phi dash, the y coordinate, and of course since we are in the xy plane, z will equal to 0. For our point where we would like to calculate, for this specific problem, we will use the Cartesian coordinate because it will be easier for us to handle it. Now we need to calculate our r. So our r, simply we need to subtract b minus m. So since we said x, y, z, so we start for x coordinate. So you will have x minus this value, which is a cosine phi dash squared, plus y minus a sine phi dash squared plus z squared. Now we need to revise this r such that we can write here, because originally we have 1 over r, so, or we can say r minus 1. So our journey from the next slide will be to calculate this r minus 1. Our journey in this specific slide is to transfer r from Cartesian coordinates to spherical coordinates. Here I just applied the square, this square and this square, and distributed terms. Then I'll gather the terms which can reduce to a spherical coordinate. For example, I gathered x square, y square, z square. Then I formed r square here. Then I gather this term and formed this term here. And finally, I gathered the remaining term, which are this one, and I formed this one here. And as you can notice, this is cosine square plus sine square. So we assume this one will reduce to 1. That's why you got a squared here. Then we can rewrite x and y in their spherical coordinate form, which is r sine theta cosine phi and r sine theta sine phi. Now just taking the common terms, so I take r sine theta in the outside here. Finally, I'll take r squared as a common term, and once we do so, we'll get here 1, we get here a over r, we get here a over r squared. R is assumed to be relatively much larger than a. We can assume that a over r squared is equal to 0. Then finally, our r squared will reduce to this form. Here in this slide, I'm going to find r minus 1. That's why you'll notice here, you have here 1 over r, because we took the root and make the reciprocal. Similarly, you will find here minus half, because we took the root and take also the reciprocal. What's left inside is the same as before. Now we will use the assumption here that 1 minus alpha to the power of minus half equal to 1 plus alpha over 2. This will simplify our r minus 1 to this form. Now, once we already know delta phi, a delta phi, sorry, which was delta L. And now we find our r minus 1. So we simply substitute with this 2 here. And once we substitute, we can rewrite as in this form, I mean our a. And at this point, we will notice that we have a term here in the direction of r and a term in the direction of j. And why we have done this one? Because we know that phi dash is a function of delta of phi. So we need to simplify as in this form or rewrite in this form such that we can accurately calculate the integration. And what I will do next is simply, because this will be a very big integration, I'll divide the integration to two forms or two terms. I1 mean integral 1 in the direction of I, and I2 integral 2 in the direction of j. So here we are solving for I1 and I2. For example, in I1, you will find two terms, sine phi dash and sine phi dash multiplied by another term, which is also a function of cosine phi dash and sine phi dash. First of all, this specific term will reduce to zero because you are integrating from 0 to pi, you can note here. Likewise, cosine phi dash here will reduce to zero because you are integrating from 0 to pi. Now we need to rewrite, so we apply sine phi dash here. We multiply inside by cosine phi dash and sine phi dash. So you get here sine square phi dash and sine phi dash cosine phi dash. Likewise, you get here cosine square phi dash multiple, and here you have sine phi dash cosine phi dash. Here we have used the relation on trigonometric, these relations, to simplify the terms here, these four terms. And what we will note here again, that we will have some terms which are integrating over a full period. All of these one are integrating over a full period, and all of this will turn to zero. So you'll find finally that you are integrating a non-phi dash component, which is sine phi. This is non-phi component, and also cosine phi, which is non-phi dash component. So we are expecting that we will just get phi dash from 0 to 2 pi. Also, this integration, of course, we have some constants outside, will result to some like this, d phi dash, which is simply equal to 2 pi. Yeah, it is written here anyway, this one. Finally, if you reformulate, you will get the value of I1 as shown here and I2 as shown here. Then we substitute back in our original A equation and not forget I and J. And once we do so, we'll find some common terms here. Yeah, here need to take outside. Further simplification, we can rewrite this term as phi. Then at the end, we will get our A equal to mu I naught S over 4 by r squared multiplied by sine theta in the direction of phi, where S is simply by a squared, which is the area of the loop. Once we have found A, calculation of H is very simple. Simply, we need to apply the curl 1 over mu curl A. Then curl is calculated as shown here. Then it's very simple. We have done this several times. Once you apply the curl, you can get the value of H, and you will find that it has some value in the direction of R and some value in the direction of theta. This equation, which is the most important now, this H equation, because we will use later to calculate the inductance caused by a magnetic dipole or by a circular loop or a small circular loop. Thank you.